Until now, we have been assuming that both the vector R and the stochastic matrix M fit into the main memory. But what if this is not true? For example, let's say that we have already encoded the sparse matrix using only non-zero entries, and therefore the space we need is proportional roughly to the number of links. For example, we can store the matrix using this format, where in each row we have the source node and its destination nodes. And let's say that we only have 10 billion nodes and we have 10 links per node, then we will need about 400 gigabytes of memory. And this won't fit into the main memory, right? But it will fit on the disk. So now let's assume that we have enough random access memory, we have enough RAM to fit the R new, the vector, into main memory, but we do not have enough RAM to fit the matrix M. And let's say that initially we stored the R old and the matrix M on the disk. Then one step of power iteration is actually very simple. We only need to first initialize all the entry of R new to be 1 minus beta over N. And then for each page, we just read into memory the following numbers and vectors. We'll read into memory the index of this page. We'll read into memory the out degree of this page, and also its destination node. Remember that we have DI destination node, and we'll also read the corresponding entry for this page I in the RO. And then for each of the destination node, we will compute this same value, this beta times R old I divided by DI, and we will add this number into the corresponding entry in the R new. Specifically, let's say that we have this sparsely stored matrix M here, then we will first read the first row, and in the first row, it's about page 0, and it has 3 destination nodes, 1, 5, and 6. Then we will first compute the number beta times RO0 divided by D0. Remember that the RO0 here is stored in the disk here. Then after we computed this number, we can then add this number to the entry of the R new here. And since we have 3 destination nodes, 1, 5, and 6, we'll add this same number into these 3 entries. You can see that we're actually adding the same number. And after that, we'll start reading the second row. And the second row will have 4 destinations, and similarly, we'll compute this value and we'll add this value to the corresponding 4 entries, and et cetera, until we finish reading the whole matrix. Now let's analyze the cost of this I/O if we use this approach. And since we first store the RO and the matrix M on this, and then in each iteration we will need to read the vector RO and M, and we'll also need to write the R new back into the disk. Therefore, the cost per iteration of the power method is actually 2 times R plus the size of M. And this is in terms of the disk operation. And one question is, what if we could not even fit this R new into the main memory? Then in this case, we'll need to resort to the block-based update algorithm. It's still a very simple algorithm. We just need to break this R new into K blocks that can actually fit into the memory. And then we can scan the M and RO1s for each block. Specifically, let's say that we break this R new into, for example, 3 blocks, and then in the first one, we'll just read the first block, and then we will scan the whole M to update this block of the R new. And then we will read the second block and we'll scan the whole M to update this new block. And similarly, we can do the same for the third block. And using this approach, since we actually break this whole RNew into K blocks that fit into my memory, and then we need to scan the whole matrix M and RO once for each of these blocks. Therefore, the total cost is actually K times the cost of scanning M and RO. So that's basically K times the size of M plus the size of R plus the size of R. And this last term actually corresponds to the reading operation of the RNew. Remember, we're breaking this RNew into K blocks, therefore we actually need to read only once in this whole iteration. So this is the total cost. But can we do better? One observation is that this matrix M is actually very large, and it's much larger than the vector R. So we must avoid reading this large matrix K times per iteration, right? And the idea is very simple. We can just break this large matrix M into stripes, and we can say that each stripe contains only the destination nodes in the corresponding block of RNew. For example, we can break this original matrix M into 3 stripes, since we are and each stripe will correspond to 1 block of the RNew. And we can see that in this first stripe, its destination is only about node 0 and node 1. And in the second stripe, it only has the destination node of 3. And in the third stripe, the destination node only contains node 5 and node 4. Therefore, when we are trying to update the first block of this RNew, we only need to scan this stripe of the matrix M, and then we can finish updating this block of the RNew. And then we can switch to this block, and we only need to scan the second stripe, and then we switch the third block, and we need to only scan the third stripe. And then overall, in this iteration, we only need to scan this whole matrix M only once. And this saves a lot of this I/O. And to summarize a bit, here in this block stripe approach, we break this large matrix M into stripes, and each stripe actually contains only the destination nodes in the corresponding block of RNew. So if we break this RNew into K blocks, we will also break this M into K stripes. And of course, we have some additional overhead per stripe, but it's usually worth it practically. And the cost per iteration of this parallel method will be the size of M times 1 plus epsilon plus K plus 1 times the size of R. So this last term is the same as before. What's got saved a lot is the first term, and this epsilon is the overhead that we mentioned about. Now, until here, we have finished the vanilla version of the PageRank algorithm. And there are actually several problems with this vanilla version of PageRank. The first problem is that it actually measures only the generic popularity of a page. But what if we want this popularity to actually bias against topic-specific authorities? For example, we only want the popularity in terms of newspaper, or we only want the popularity in terms of movies. How can we do it? And the solution is what we call topic-specific PageRank. And we will talk about this in the next lecture. The second problem is that this PageRank only uses a single measure of importance. And in the next lecture, we'll talk about other models of importance. For example, we'll talk about the Helps and Authority method. The third problem is that this method actually is very susceptible to link spam, because people can have artificial link created in order to boost the PageRank. And in the next lecture, we'll talk about a method called TrustRank to combat this problem.